And then maybe you can share your screen, and then we can at least see the problem.
It says host disabled participant screen sharing.
Oh, okay. Well, I disabled participant screen sharing, I guess. So I'll share my screen and I'll write the problem down.
Okay.
Okay. Let's take a pause here. Do you think the camera would look better like this if I mean, I had to rotate it, but like, it seems this would be easier to read if it were rotated. So let's actually do that. Nope, that's not it. So is this easier to read than on the side?
If you make it full screen.
Yeah, it's going to be full screen, but.
Yeah, I think so.
You think so?
You might have to move your paper around a lot if we're like going back and forth between notes. But that's about all.
Yeah, because I think when it's on the side, it has this weird like stretching on the end of it. So let me rearrange my desk setup a little bit to accommodate this new setup we just thought about. How's that?
I think that's good.
Better? Worse? We can go back. Any?
It's not stretched, but only so much of the page can fit onto the screen.
Yeah, but that was the case before too.
Then I think it's good.
But I don't know how I'm going to move it forward though. Yeah, that was not super well planned. I think it's got to go back here until I find another way to keep the camera up when I can slide paper under it. Sorry about that. Testing. Okay, well, back to exactly where we were, but we learned something, I guess. So we want to evaluate this on the curve, and we have a parameterization given by R. So what are we going to want to do?
So I found R prime of t.
R prime of t is it is.
Are you asking?
Yes.
Oh, 4t cubed plus 3t squared.
That's R prime of t. So what we want to do is evaluate our field, which is this, on the curve, which is this. So what should I do? Well, so where do my bounds go? They go from 0 to 1. And I need to evaluate f on this curve. So what should I get?
So you plug in R, you do like f of r of t,
Yep. So what is f of r of t?
e to the t to the fourth minus 1, plus t to the fourth times t to the seventh, I guess.
And I'm going to take this dotted with 4t cubed I plus 3t squared j dt. Okay. Take the dot product. I get 4t cubed e to the t to the fourth minus 1 plus 3t 79 dt. Okay. And I just evaluate this integral. Split it up in the sum. This one's nice and easy. It's a polynomial. And this one is integration substitution. Very quick substitution right here. The derivative of this is equal to that. So a quick u substitution should do.
I have a question.
Yeah.
Why exactly do we dot r prime of t with f of r of t? I remember we talked about it last class, but I'm just curious as to why we dot it.
Well, when we talked about work at the beginning of the semester, what is work? Work is the force dotted with the displacement vector.
Okay.
Right? So dr describes our displacement vector. Right? It's that the derivative r prime is the tangent vector, which describes direction, and the dt part describes how far you go, length. So f dot dr is work, the force dotted with the displacement vector. That's from a sort of heuristic why we do it, but from a computational practical sense, how do we take the integral of a vector and get a number? We don't.
That's right, yeah.
We need to take the integral of a number to get a number, or a function to get a number. So I want one function, not a vector valued function. So how do I get one value, one function out of two vectors? I take their dot product. Okay. Any other questions? We don't need to compute this, do we? I mean, we can go about that. Did that answer your question, Nick?
Yeah, it did.
Okay. So the part B. Okay.
I didn't compute it either. I just got to that point and left it.
You should compute it. It's not a very hard one to compute. It was designed well. This is an immediate use substitution. You could probably do this faster than it would take you to put it in the computer. So this is, and so this is, I think, the beginning of some of the really cool shit you talk about in Calc 3 or whatever calculus. We're vector calculus now. So we have been very familiar with something called the fundamental theorem of calculus. Fundamental theorem of calculus. Calculus. Okay, glad I don't have to spell calculus often. So, and what does it say? It says, well, the integral from a to b of the derivative with respect to t is equal to the function evaluated on the endpoints. So nothing new, but I want to describe this in a different way, and that way will be how we think about the fundamental theorem as we move forward. And I've said multiple times, there's really one fundamental theorem, and they all have the same, well, they're going to have many fundamental theorems, name-wise, but they all have the same fundamental idea. Okay, and in fact, they're all applications of Stokes' theorem. So there is actually one fundamental theorem. But what does this say? This says that I can take an integral over the interior, right? So I've got some picture. This is A, this is B. This quantity right here, this is the integral, A to B, f prime of t, dt, right? That's what this number means. It's the area of the shape. And so this integral here describes the integral over some region, right? The interior of that region. Whereas this quantity here, this is evaluating the boundary. So we can relate this whole thing to a different function evaluated on the boundary. So what I want you to take away from this discussion is the fundamental theorem translates integrals over a region or the interior of a region to computations on the boundary. Okay? Notice what happened. We removed one integral when we moved to the boundary. And at the cost of one integral, we also undo a derivative. That's very, very highbrow and not super technical, but we'll see it play out in many different places as we move forward. So remember what we're doing here. We're taking an integral of a function that happens to be the derivative of another function on the interior of a region, and then comparing that to the original function on the boundary. Okay, the fundamental theorem translates stuff from the inside to the boundary.
Could you say that one more time?
The fundamental theorem translates information about the function on the inside to stuff on the boundary. Okay, and we can see that by this integral, this interval is what we're integrating over, but we only need the values at the ends to compute this integral. Okay, and why is that important? Sometimes the stuff on the boundary is easier. It's some lower dimension, obviously. This has infinitely many points in here. I only really need 2 of them on this interval to talk about the fundamental theorem. Okay? So when we talk about other objects like this, we're going to talk about a different fundamental theorem right now. Remember what it's doing. It evaluates the integral on the interior and converts it to a quantity on the boundary. Okay? And I'm going to write that right here. Right here. This is what the fundamental theorem of calculus essentially does. Okay, this is what all fundamental theorems of calculus will do, whatever object you're talking about, in whatever dimension you're talking about. So let's talk about the fundamental theorem of line integrals. So what does this mean? Let's look back at, first, let's say I don't have a fundamental theorem of line integrals. We haven't come up with one yet. And we want to make one that's essentially just like the fundamental theorem of calculus. How would I do it? So what does this say? It says, well, I have a derivative and it's not derivative, right? So in higher dimensions, what operation describes the derivative? That's a question to you guys.
What operation?
Yeah, what describes the derivative of a function in higher dimensions now?
Like dx dt or?
Well, that's okay. That's still the same thing.
Yeah.
If I have a function in one dimension, its derivative is another function, right? So in higher dimensions, if I have a function in two variables, what object is its derivative? The derivative
A surface?
is replaced by, come on, someone else needs to think. There's 5 of us here, 6 of us. What replaces the derivative? How about the gradient? The gradient is the vector that is comprised of all the partial derivatives. So the gradient, as we said, is a vector field. And if I have a function, I could take its gradient and it should act like the derivative in the sense of it tells me how the function is changing. That's what the derivative tells us, right? The gradient tells us how the function is changing. So if I were to translate the fundamental theorem into line integrals, I would replace my derivative with my gradient, right? And I would need to replace the endpoints with the endpoints of my curve. So if I have some integral, gradient of f dot dr, right? I'm taking the integral of the work done by the vector field gradient of f, right? What should this be? This should be the function itself.
Is it like but your gradient is with respect to x, y, and z, or however many variables you have.
Yep.
So do you put your r of t into each of those, like f of x, f of y, and f of z?
Yeah, if you want to evaluate this integral, yeah. You evaluate it the exact same way. There's nothing different, right? But this theorem, this should look exactly like the fundamental theorem, because it is exactly like the fundamental theorem. Right? I take the integral of the derivative over the whole region. It's equal to the antiderivative on the boundary. Right? What is R of B? R of B is the endpoint of this curve. And R of A is the beginning of this curve. So this is exactly the endpoints of my curve, the endpoints of my region. Does that make sense?
Are A and B like on R of t?
A and B are not on R of t, right? T is time, and A and B are times. R of A is a point at a specific time, A. Everyone else should turn their cameras on too, so we can have this like dialogue. I feel like I'm talking to Nick here.
Great one-on-one class.
I know the rest of you guys have cameras. There's so few of us, we might as well turn them on. Okay, well, that's one person. I will continue asking. So if you don't want me to keep asking, you should just turn them on. So does this make sense? Let's say, does this make sense in what you expect it to be if we're going to generalize the fundamental theorem?
I don't feel like I understand what's happening.
Okay, so we literally just did this question right here. Right, and we computed this integral. Right? We computed this the old-fashioned way, right? We parameterized the curve, we took a dot product, and we computed this integral, right? But what I'm saying here is we don't need to do this part here or this part, because if we have a compute, this is another, imagine we want to compute this integral. This is exactly like the one we just computed. This is a vector field, and this is the dot product, right? We just computed one just like this in that homework problem you talked about. So if we do a parameterization of C, which we have R, we don't need to compute the derivative and take the dot product and actually evaluate this integral. All we need to do is find the function that this is the gradient of, and then evaluate that function on the ends of my curve.
Yes, okay, I see what you're doing now.
Right?
So you're getting rid of the integral in and of itself.
Yeah, I have removed the integral over this region, which is all of C, and replaced it with evaluating a different function on the boundary, right? The boundary is just two endpoints, just like in the fundamental theorem. Okay. Does that make sense?
Yes, that makes sense.
So let's see this in practice. Let's look at this example here. This is a pretty standard example. F of x, this is the force this is the gravitational force field. So if I'm a particle of mass lowercase m, and the Earth has mass capital M, and this is the gravitational constant, this is the force, the vector field associated with the gravitational force of the Earth. Okay? Vector field of gravitational force of an object of mass capital M. Okay? Pretty commonly used as Earth, for example. Notice the negative sign here. It says it's pulling things to Earth. Okay? Away from Earth is positive. Towards Earth is negative. So I want to compute this integral. So what is the work done on a particle that moves along this curve? It goes from 3, 4, 12 to 2 to 0. Okay, you can't see that. Okay. So we're going to want to use the fundamental theorem to do this. And to use the fundamental theorem, what do we need?
Can you go back real quick, Professor? Just to the coordinate. Thank you.
So to use the fundamental theorem, so right here, what do we need? We want to compute this integral. We have this. So we need to find what f is, right? We want to find a function whose gradient is this vector field, right? And we can do that. I'll just give you the answer, and we'll see how we go about that in a little bit. So note that f of x, y, z equals m capital G, G square root of x squared plus y squared plus z squared has the property that gradient of f is f. So you can go compute this if you like, but if you take the gradient of this, you're going to get this field right here. Okay? Okay. Does that make sense? So now let's use the fundamental theorem. So what does it tell us? That I can compute this integral by looking at this function and evaluating it at the endpoints. What are the endpoints?
You're asking what A and B are?
A and B are times. R of A and R of B are points.
So R of A and R of B.
Notice there's no notion of time here.
Yeah.
All I said is the curve goes from here to here.
Well, would those be your points then? Or
So these are my points. Which one is which?
First one is A and the second one is B.
No, this is a point. A is a time in this equation, right?
Yeah, so you plug those points into your equation and you get
So
a time.
this right here is R of A, and this right here is R of B. I don't care about what A and B are. I care about the points, right? I use A and B to parameterize my curve if I need to parameterize my curve. But if I'm already given the points, I don't care what time I arrive at those points, right? So all I need to do is evaluate this at these points, 2, 2, 0, and 3, 4, 12. Okay. Does that make sense?
Yes.
And so now we can actually compute this. This is very easy to compute, right? This integral of this very complicated vector field, G length of x cubed x vector dot dr this is equal to this one, which is m capital Mg over 2 squared plus 2 squared is square root of 8 minus m capital Mg over 3 squared plus 4 squared plus 12 squared. I think that's a Pythagorean triple. Well, square root of 9 plus 16 plus 144. I think that's 13 cubed, 13 squared. I think that's 13 squared.
Yes, 13.
Yeah. mmg over square root of 8 minus mmg over 13. Okay, so let's take a step back and think about what we learned here, or what we did here. We computed this really complicated integral, right, over any curve C. I didn't pick a parameterization. I didn't even tell you what C looks like. All I said is it goes from here to there. Right? There's no notion of what C does. All it says, or how C looks, or what the curve is. It only says it goes from here to here. Does that make sense?
You're able to do this because we use the gradient vector.
We're able to do this because we use the gradient vector.
Okay.
Because the field I have is a nice field. Okay. So we're going to talk about nice fields. They talked about this in section 6.1, but I didn't think it was the appropriate time then, since they didn't really use any of it. So, question, Nasser?
Yeah. Like, I understand the whole process and everything, but why would we have to like do a traditional integration if we could just do this? Yeah.
Well, there are a couple reasons. One, we can't always do this, and we'll talk about why we can and can't do this, right? In the notions of physical problems, we can almost always do this, right? Physics, well, we'll talk about special fields in just a moment, but most fields in physics, electric fields, gravitational fields, magnetic fields, all are special that satisfy these equations, right? So you really don't really need to do this in many physical cases, but there are many other fields that don't satisfy these equations.
Okay.
And they make perfect sense to study. So let's look at these kinds of fields. So what fields are we talking about? This worked because the vector field of interest right here is the gradient of another function, right? 5. This works because the vector field is the gradient of a function. This only works because of that reason, okay? And these kinds of fields are special for that reason, and we call them conservative fields. A field, vector field, sorry, that is the gradient of a function is called a conservative field. Okay, and the function that it is a gradient of, the function it is the gradient of is called the A potential function.
Aren't all I guess like or like say you have like some sort of function that has some I, J, and K components. It can have a gradient. Like any of them will have a gradient.
Well, that's okay. I think we're a little confused here. If I have a vector valued function, it doesn't have a gradient, right? The gradient is the gradient vector for a function with one output,
Oh, okay. All
right?
right.
So if I have a function like this, f of x, y, z equals something called w, and if w is a scalar, then I can talk about the gradient of f, right? But if w has multiple
Variables.
variable, if w is a vector itself,
So,
then it will have a gradient. It doesn't have a gradient, it has a Jacobian, which is a matrix, not a vector, right?
okay.
So we talked about that slightly in 15, end of chapter 15. Okay.
It feels like we have an integral over some curve C of gradient, the gradient of a vector times or dotted with dr.
The gradient of a function.
The gradient of a function dotted with dr. And it feels like you're trying to say that we need to find the function that turned into that gradient, or the
Exactly. That's exactly what I'm saying.
yeah.
Yes.
And that is called a conservative field.
The field. Okay, I see that. I see the issue here. Given a field f, if I can find a function whose gradient turned into that field, it is conservative. But that doesn't always happen. So what I mean by that is there are vector fields, which we'll talk about, that have no functions whose gradient is equal to that field. We've been very nice in seeing fields that are always conservative, but that is not always the case. So, for example, last week when I came up with this random line integral, and I said these two things do different things, and they did the same thing, that was lucky because they were conservative. And they both happen to be 0. But that's not always the case. So we will see fields that are not conservative fields. Meaning, no matter what function I pick, I will never be able to get that function's gradient equal to my field.
Okay.
Okay?
Interesting.
So this goes back to Nasser's question of why do we do integration if we have this theorem? It doesn't cover non-conservative fields. Okay? Does that make sense? So we're familiar with what a conservative field is and a potential function is. The reason this is called conservative fields, a conservative field, is because this goes back to an application of this is proven conservation of energy, which means that in any system, the total energy is fixed. I can't add or remove energy. So the sum of the kinetic energy and the potential energy is always the same. That is why it's conservation of energy. Okay? So let's look at something that we kind of skirted under the rug. And it's called path independence. And so why did I say we skirted this under the rug? If we look back at this problem, all we did was move from this point to this point. I didn't tell you how we got there. Right? I could have gotten there any way. I could have done this or straight there. I could have taken a bunch of loops and gotten there. But because of this construction right here, I only care about the endpoints, not the stuff in the middle.
Don't you need to care about it though? Since we're talking about like distance?
So the magical thing is I don't. If I have a conservative field, it doesn't matter how I get from point A to point B. The work done by that field is the same, only depending on location.
So a non-conservative field,
It does matter, yes.
Oh,
But like I've said already, we are very used to conservative fields. The electric field, magnetic fields, and gravitational fields are all conservative fields.
are there any examples of non-conservative fields that are like known? Or
Well,
prevalent?
there's lots of examples of non-conservative fields.
Yeah.
I don't know of a physical field that is not conservative, though. Yeah, I really, an obvious example, which is not really that interesting, would be like, imagine I have a jet turbine right here, and I look at the field that is the airflow at any given spot, right? It's going to be really long here, like behind the turbine, right? And essentially zero over here, right? Because the turbine isn't pushing anything over here. So this whole thing doesn't really describe the derivative of a function. So yes, but in theory, I wouldn't be interested in shit over here anyways. Yeah. So yes, there are many non-conservative fields. I can't think of one off the top of my head that's actually interesting. So I'm going to write that down because this is very important. If F is a conservative field, due to the fundamental theorem, the curve C doesn't matter. Just the endpoints. That's what makes this theorem really nice. We don't care about the curve itself. So if someone gives you this hideous curve, for example, this is A and this is B, and I have some hideous curve. And my vector field is conservative, computing this line integral is exactly the same as computing that line integral. Does that make sense? And that's why this area is off you can't see that picture, but that's why this is called path independence, because it doesn't matter how I get from point A to point B. It just matters that I was at point A and I ended at point B. And if I have a conservative field, the work done is the same. Okay. Does that make sense?
So we can now use this instead of like all the other stuff we've been doing for integrals, or
That's the point. I mean, that's why you make theorems like this, to use them, assuming you have a conservative field. So there's still that discussion of how do I check if my field is conservative, and that will be coming soon. Okay. So I'm going to write down a formal definition of what we just talked about here. It says, if F is a continuous vector field, the line integral is path independent if the integral for all curves C1 and C2 that have the same initial and terminal points. I just wrote down what we just talked about. Okay. It says, as long as the two curves start and end in the same place, their integral is the same, no matter what happens in the middle. Okay. Conservative fields have this property. Okay.
Is that a minus?
Where is there a minus sign?
Integral C1, yeah.
That's an equal sign. Okay. And I just want to say that this integral, this equation, describes exactly what we just said. We're trying to put symbols, equations to what we're talking about. Okay. So why do we care? There's a couple interesting things that happen here. So what if C starts and ends in the same place? Right? So I have some vector field. It does this. This is A and B. Well, R of A, R of B. Now I see why the confusion of A and B is times and points, because sometimes I use them as points and sometimes I use them as time. But I'll try to keep them as points here. R of A and R of B. What should this be if my field is path independent? If the integral is path independent?
Wait, what?
What should this, let's say this is C. What is, if this is my curve and I start and end at the same place, what do you think this integral should be?
0.
0. If it makes perfect sense to be 0, right? Because I didn't go anywhere. I literally just said right here, it doesn't matter how I get there. All that matters is where I started and where I ended, right? If I start and end in the same place, I didn't go anywhere. The work done should be 0. That's the same. That can be also described by this equation. If these 2 points are the same place, then this is 0, is it not? So if the integral is path independent, this will for sure be 0. If you're tracking the book, this is theorem 3. So it says, I'll make a new page here. 7. Integral over CF dr is independent if and only if integral CF dot dr equals 0 for every closed path C. A closed path is a path that starts and ends in the same place. Okay. Okay, does that make sense? All it says is if my integral is path independent, this can only happen if I get 0 when I go in a circle or a loop or whatever convoluted thing I want to go to. As long as I start and end in the same place, I'll get 0. Okay? We already know that conservative vector fields have this property. So conservative vector fields are path independent. And if I have a conservative vector field, any closed loop will produce 0. Right, so if you remember back in physics, you always say work is the force times the displacement. And if I don't go anywhere, my work done is 0, right? That's because work, gravitational field, is a conservative vector field. So going back, I'll say that again, the gravitational field is a conservative vector field. So if I start and end the same place, the work done by the field is 0. Okay? Note that conservative fields are path independent. I know this is a bit of like highbrow theory for a little bit, but we're going to use some of these theorems next in just a couple minutes. Okay? Does this make sense for now? Going to take another pause here. Bob and Darius. Cameras on, please. There's Bob. Darius is hiding out in the dark. Maybe he's not paying attention. Maybe he's not even there. Yeah. So let's move on here. Let's see. So we know this. I just wrote this. It says conservative fields are path independent. Conservative implies path independence. When can we go the other way? So if I have a path independent integral, how can I determine if the field is conservative, right? Because this goes back to my first question, or all of our first questions. Nasser said, why can't we always do this? There are non-conservative fields. And Nick asked, what are non-conservative fields, right? So this goes to the answering the question of how do we determine if something is conservative or not, right? Because being conservative is a very powerful thing. It gives us all of these statements. It allows us to use the fundamental theorem. It tells us that all path integrals, all line integrals are path independent. So now if I have a path independent line integral, does that guarantee that my field is conservative? What do we think? Do we understand the question well enough to appropriately guess?
I mean, I don't think so. It's not enough information to guess it's conservative.
Okay.
It's a part of the Yeah, it's just a part of the information, I guess.
I can give you a guess if you want one.
Okay. Well, the answer is no, so that's a good guess. But what do we need? So let's think about what we need. If it's very close, it's most of the information, but we need to make sure, let's think about this in a highbrow heuristic sense. We need to make sure that it's path independent over a nice enough region, right? That seems pretty reasonable. As long as it's path independent over a nice region, then that is path independence should guarantee conservativeness.
What do you mean by nice region?
Yeah, we're going to talk about nice in detail here. And nice has a lot of really complicated things in math, in particular this kind of math. So we will attempt to talk about nice.
The mathematical definition of nice?
One of the many mathematical definitions of nice. Okay? There are many of them. Mathematicians like to use words that are very common in English and give them very technical meanings, like the word almost or open or things like that. There is a very strict definition for the word almost in this kind of math. Okay. We won't have to deal with almost, but be aware of those things. Almost has real meaning in math. Okay, so what are we going to talk about? If is path independent on a nice region, then F should be conservative. Okay, so what does nice mean? So if I were to give you a region, okay, how about I'm going to draw two regions. You tell me which one is nicer. If this is the first region and this is the second region, which one is nicer?
The first one,
The first one. Why?
it's like connected.
It's in one piece, right? It's connected. So we will call these kinds of regions connected for the obvious reason of they're in one piece. And these are not connected, right? So, but I do want to make a disclaimer. If you do look at other texts, this is not the correct definition of connected. This is what we're going to talk about now is more commonly referred to as path connected. Because if I'm here, what I mean by path connected is any 2 points in my region can be connected by a path. Whereas if I'm over here, this is not path connected because I can't connect these two with the path that's in my region. So the book will refer to them as connected and often will refer to them as connected. But in other areas in calculus, it will refer to this as path connected.
Is there a major difference between path connected and connected?
For our cases, no. But in general, yes. So that gets into the complicated definition of what connected actually means, which we won't talk about at all. So for our discussions, think of path connected and connected as the same. But I'm bringing this up is because if you look somewhere else and you go online or look at some other tutoring materials, they may use the term path connected because this is technically path connected, okay? So obviously, this region is much nicer than that region. Pretty straightforward. I'm gonna draw 2 more regions and you tell me which one is nicer. So the region is this with this open boundary, or this with some of this open boundary and some of this closed boundary.
Probably the completely open one.
Yeah, right? This seems to be much nicer than this because this has this weird hard edge that we have to deal with, right? So this is an open set, and this is a closed, or not open set. I'm going to say that. Closed and open are not opposites in math. But so when we mean an open set is just a set with no boundary. Okay? So what does a nice set mean here? It's going to be open and connected. A nice set is open and connected. Okay? So what does that mean? It's in one piece and there's no boundary pieces on it. Okay? Any questions?
What does that say? It says a nice set is
Open and connected. So with that in mind, let's go about talking about nice sets. And it says, this is theorem 4. The book has some good proofs about these theorems. I really recommend reading them, but I don't think we're going to go through them. Okay? It says, if F is a continuous vector field on an open connected region D, I guess this is a bad sentence, but so we have a continuous vector field on an open connected region. If integral CF dr is path independent in D, then F is conservative in D. So what does this mean? Theorem 3 and theorem 4 together say, if I have a continuous vector field on an open connected region, then being path independent is exactly the same as being conservative. Okay, so how do I use that? I can say, well, if I don't have path independence, I definitely don't have conservativeness. Probably should have thought of a better adjective for that, but okay. This discussion of D is going to be pretty reasonable because these are the kinds of regions we talk about anyways, without thinking about them, nice ones. No one goes and imagines some weird blob in a bunch of different pieces. Okay. Any questions about this?
You could still, something could still be path independent or something like that, even on like a not open set, or like it could be not connected too, right? You could still do the same thing,
Yep.
even if it's no.
You could.
Oh, you could.
Yeah, you could definitely have path independence on non-connected sets.
They're just harder to.
They're just different to describe because
Okay.
you have to. I mean, no, they're not different to describe. They're harder to actually deal with because you have to be careful about where your path is going.
Mhm.
Right.
Okay. No, I was just curious.
Yeah. Okay. Does that make sense? We're almost to the point where we can actually answer the question, when is my field conservative? Okay. And we'll be able to check with something really easy. That's the best part. All this really complicated theory comes down to a very simple check under some nicer circumstances, okay? So how do we check? How do we tell if a field is conservative? So let's think about this. If F is conservative, I'm going to write F like this. For our illustration, we'll do this in 2 variables, but we can do this in higher dimensions as well. That's not super important. Right? We've got a vector field. It looks like this. And I want to determine if it's conservative. Okay? So if this is conservative, what does that mean?
It's path independent on some.
It's path independent, true. But let's something even simpler. If this is conservative, that means that it is the gradient of some other function, right?
Yeah.
Then there is some f xy such that gradient of f equals f. That's literally what conservative means, right?
So there should be some operation, like kind of like antiderivative, where you find the anti-gradient or something.
Yeah,
like that.
there is. I mean,
Oh,
it doesn't have a name, but yes. And we'll talk about doing it, and then we'll talk about deciding when we can do it, right? So if this is a conservative field, there's this function f, right? And what do we know about functions like this? In particular, what should happen here?
so it should be equal.
These should be the same if the
Yeah.
partial derivatives are continuous, right? Should be. And so what does this mean here, though? If f is the gradient of lowercase f, what is p here?
Yes. Or um. That's the dftx.
Yeah,
Right.
this is the derivative of lowercase f with respect to x.
Yeah.
And this is the derivative of lowercase f with respect to y, right?
Yeah.
And if I expect this to happen, what do I really want to check? All I need to check is dp dy. This should be equal to dq dx. Right? Because p is a derivative with respect to x. So if I take the derivative with respect to y, I should get the same thing as the derivative with respect to y and then the derivative with respect to x.
That makes sense.
Right? So if I have a description of my vector field like this, I can quickly check if it's conservative. Well, I can quickly check if it's not conservative, if it fails this equality. Right? Does that make sense?
Wait, what? dp dy,
Mm-hmm.
that is the derivative isn't p the
This is an equal sign. P is a derivative of, let's just write it down. P is df dx, right?
oh I see.
So if I take the derivative of p with respect to y, I get this thing.
Yeah.
And q is df dy. So if I take the derivative with respect to x, I get this thing. And they should be the same.
But I'm confused as the dy and dx that are underneath dp and dq. Wouldn't it be like, I don't know, I'm just confused as to why there's dy and dx underneath
Okay, so
q.
p is a function, right?
Uh-huh.
So this is what p is. It's a derivative of f with respect to x. But there could be y's and z's in, well, there's no z's in here, but there could be y's in here, right? So p is a function of multiple variables, x's and y's. Correct?
Yeah.
So y, it makes perfect sense to be able to take the derivative of p with respect to y. P is a function with respect to y, is it not?
Yeah, it is. I think I'm just confused on how like the second derivative of f over dx dy is equal to dp dy.
So what is p? P is by definition the derivative of f with respect to x.
So just df dx.
Yes, p is df dx.
And then to take the derivative of that with respect to y.
Yep.
Okay, never mind.
Yeah.
Now it makes sense.
We're literally just doing basic partial derivative stuff here.
Okay, I get it now.
So what does this say? This says that, what does it say? This says, if conservative, then this stuff happens. Okay? So we can check if something is not conservative very quickly by checking if it satisfies these equations. If it fails these equations, it can't be conservative. Okay? So if does that make sense? So let's look at an example. I'm going to make this random example up, but say f is xi plus xj. Okay. Is this conservative or not? Is f conservative?
If we treat xi as p, and then
X is p.
sorry, if we treat
So
x as
p is equal to x and q is equal to x.
and then
dp dy is
xy, or
what's the derivative of this with respect to y? Sorry.
just x, or
0.
0. This has no y's in it. 0. dq dx is
1.
1. Is this vector field conservative? No,
not conservative because those aren't equal.
they're because they're not equal. Okay. Does that make sense? This is a very easy check to rule out non-conservative fields. I mean, it's as simple as taking two derivatives, which we're good at most days. We should be good at most days. Right?
So knowing that it isn't conservative, that helps us with
Well, it doesn't really help us per se. Well, it does help us. It tells us that we can't use the fundamental theorem. So we got to go do something else. That's what it tells us.
If we did find out that it was conservative, then we could have used the fundamental theorem.
Yeah.
Yeah. Okay.
So, but it's not conservative, so we can't use the fundamental theorem. We got to go do something different, right? Okay. Does that make sense? Very quick and easy way to check if something is not conservative. Okay. So let's ask what happens the other way around. Right? So if these equations are satisfied, is that enough to guarantee that our field is conservative?
Guarantee that it's not conservative?
That it is conservative. So these equations, it says that if I'm conservative, I have this to be true. But can I turn the arrow around and say, if this happens, I have a conservative field? Another yes or no question. What do we think?
Wouldn't you also check if it's path dependent and then say it is conservative?
Okay, well, that's one way to do it. If it's path independent over a nice region, it's definitely conservative already, right?
Yeah.
So I don't need to check the derivatives at all. But checking path independence is very hard, right?
Yeah.
What does that mean? I have to check every single possible path, which is much harder than just checking two derivatives. Correct?
Yeah.
So that's a very reasonable point, but from a practical standpoint, I'd like to be able to check two simple derivatives, right? So, I mean, from the way I pose this question, the answer is probably no.
Yeah.
But what do you think we need to make the derivatives enough to satisfy conservativeness?
More information about the...
Yeah, what more information do you think we'd need? What more information did we need last time?
What if?
Last time we need to know if it was path independent and in a nice region.
In a nice region, right? So this time we're replacing the path independence with the derivative condition, right? Because those are things we're checking. Now we just need to replace the nice region with a different nice region, an even nicer region. Okay? So if we have the derivatives in a really nice region, we're guaranteed to be conservative. Okay? And let's write that down. So let's talk about nice. Imagine this is open. Is this region nicer? Or is this region nicer?
I'm gonna say the second one is nicer.
Why is the second one nicer?
Something about...
Let's vote. Let's guess. Who thinks the first one is nicer? Seems to be nobody. Why do we think the second one is nicer?
It doesn't have a hole in it.
It doesn't have a hole in it. Really simple shit, right? The previous discussion was it's in one piece. And this discussion is there's no hole in it. Right? Okay, so there is a very simple mathematical way to describe this no holes condition, right? So this region is simply connected. So not only is it in one piece, it's in one piece with no holes. Okay? So what should the theorem say? It should say something like, if F is a vector field on an open, so I still need the open condition. And instead of connected, I'm going to be simply connected. So connected with no holes. Region with dp dy is dq dx. Then F is conservative. So if the derivatives match up and my region is nice, then I'm guaranteed to have a conservative field. Okay. Does that make sense? And what's nice about this theorem? This is theorem 6.
So is simply connected region our even nicer region?
Yeah, it's an even nicer region. But I want to point out that nicer and nice are essentially obvious, right? Because who in their right mind is going to draw a region like this and say, do math over this fucked up thing with a hole in it?
Hey, you'd be surprised, man.
I know. People, this happens. But really, when we think of regions in the plane, we think of regions like this. Smooth, connected, no holes, no crazy pokey points. I understand all the other ones do exist, but we intuitively think of the nice regions. Okay? So what's nice about this theorem? This is really, really, really easy to check. I mean, we're just taking two derivatives, right? So let's look at an example. Is F conservative? Well, F is 3 plus 2xyi plus x squared 3y squared j. Is X conservative? Let's try to use theorem 6. What do we need to check?
If the first one is P and the second one is Q, then we take that, the first one with respect to Y.
Okay, so what happens when we take the first P with respect to Y? dp dy is
You only get 2.
we get what?
You get like 2.
To x.
Just 2x, yeah.
Correct.
This is y, and this is derivative. Okay, derivative of this with respect to y is 2x. This has no y's in it. It's 2x times y. And what is dq dx?
2x.
2x.
Yeah.
Right?
Those are
So their derivatives match. Do they match on a nice region? A nicer region?
do we pick our region or do we?
We could. We don't have to, though. The point is that where is this vector field defined?
There. Oh, those two.
No, it's defined anywhere. defined as in what
Oh.
values of x and y can it take. It can take
Oh, I
any
see.
values of x and y.
So if it had been like ln of something or like,
Yeah. If it had been natural log of something, or there's some weird square roots in there, or I
Yeah.
divided by something, I'd have to worry about things I couldn't take, right? But I can take any value, right? So I can take anything from R2. X and Y can be anything. And R2 is definitely simply connected. Does that make sense?
yeah.
It's the nicest region we can think of. It's infinitely large, but it's infinitely nice. Sort of.
So we talk about like nice regions and stuff, but what if we just did all real numbers, like
Yeah,
going
that's-
out and
That's perfectly fine. That's a nice region.
oh,
And in many cases, that's what's going to happen. There's only a couple things that we can do to actually make the function not continuous, right? We need to divide by 0 or have some natural log stuff going on or something like that, right? As long as we avoid those things, our domain should be simply connected because it's going to be the real numbers.
so we can have like a vector field that is conservative in all directions for an infinite.
Well, okay.
Not
Conservative
sorry, not a vector
is,
field.
is not a description of any direction. Okay, so conservative is the description of the field itself. So think about the field, a conservative field doesn't depend on direction. That's the whole point of it, right? The motion of the field itself is conservative. The forces in the field itself is conservative. Okay. Does that make sense? So now we have a very easy way to check if a vector field is conservative or not. Okay? Now, what is the last thing we need? Let's say I have this giant stack of papers. I have this part. I know it's conservative. What do I need to solve this integral?
Points?
Let's say I have those points
Oh.
because I have C, right? So I definitely have those points. What am I missing?
Direction vector?
I'm missing F. Knowing it's conservative is one thing, but what is it the gradient of?
The anti-gradient.
Yes, we need this thing called the anti-gradient, which is not a thing. Don't start calling it that. But that's essentially what it is, right? I know it is conservative. What is its anti-gradient, I guess? We should probably think of a better term for that. I don't know why we hadn't come up with a word for
I'm
that.
pointing it. I'm gonna textbook.
Yeah, sure. So if we know it's conservative, we can check if it's conservative very easily with this theorem. How do we find the function that it is the gradient of? Right? If f is conservative, what function f makes gradient of f equal to f? So now the question is, how do I find f, right? Okay, so let's go through an example here. And the reason that the reason I don't want to call this the anti-gradient or whatever, or the reason it probably doesn't have the name anti-gradient, because all it is just integration. We're just going to integrate a couple times. Nothing special, nothing fancy, okay? So I have observed through this day that our basic calculus skills are not extremely awesome. We should brush up on them, especially basic integration and basic derivatives, because we're going to be using them a lot here. Okay. So let's go back to this function. Given f equals 3 plus 2xy, I plus x squared plus 3y squared j. I want to make sure, I want to find the function that has this as its gradient, right? So this is p, which is also df dx, and this is q, which is df dy.
If we take the integral of p and q, will that give us a?
Yeah, it's not rocket science.
Yeah.
If this is the derivative, you should just take the integral.
The
right?
integral of it, yeah.
So if I take the integral of p with respect to x, integral 3 plus 2xy dx, what do I get?
3x plus x squared y. Yeah.
But there's something missing.
Constant.
A constant, yes. But even more than that, it's a constant with respect to x, meaning this could be an entire function that has a bunch of y's in it. Because if I take the derivative again with respect to x, I get 3, 2xy. This has no x's in it, so it goes away.
Yeah.
Right? So
Yeah.
when I integrate, I not only get a constant, but I get an entire function that doesn't have x in it.
What do you do about that?
Well, let's think. If I integrate this thing, and I get this is supposed to be f, right? If I take the derivative with respect to y, what should I get?
You mean take the derivative of your p?
Of f with respect to y.
And you should get q.
I should get q.
Yeah.
Right? So I find f, well, a possibility of a structure for f. I take its derivative with respect to y, df dy. This is, what's df dy here?
3 plus of that.
Of this right here.
Just, yeah, x squared plus g of y? Or
Plus g prime of y.
g prime of y?
Right? And what is this supposed to equal?
Oh, that should equal df dy. Or dp, or dq dy, or whatever it is.
Okay, so tell me what's supposed to be on this other side of the equal sign here.
That with respect to y, so 3xy plus
Q is the derivative of f with respect to y, right?
okay.
Q is the derivative of f with respect to y, and this is the derivative of f with respect to y. So this should be an equality. Does that make sense? Yes? No? So let's start from the beginning. If this is f, we know that p is the derivative of f with respect to x. And q is the derivative of f with respect to y, whatever f is, right? So I found one possibility for f. I know f looks like this. I integrated p with respect to x, right? It looks like this. But since it looks like this, And I know if I take the derivative with respect to y, I have to get this. Because q is the derivative of f with respect to y. So I took the derivative of this whole thing with respect to y, and I got this. But I know this is equal to this, as we just talked about. Right? So that says that these x's can cancel, and I get g prime of y equals
3y.
3y squared.
So the 3y squared part of our q, or
Mhm.
not our q, but like
Of q, yeah, right here.
of q is the other part of p that we were looking for.
Is the derivative, no, it's not part of p. It's the part of f that we're looking for. It's the derivative of the part of f we're looking for.
And that's the same for regardless of what function we have.
This is, well, this is the function we have. We have a function whose derivative is equal to this. Right? What functions have derivative equal to this? If g prime of y is equal to 3y squared, then g of y is equal to what?
Y to y cubed,
Y cubed plus
g prime of x, or
a constant. This has no x's in it.
that's the constant. Like that's just
Yes.
a pure constant.
This is now just a constant because I know that g right here can't have any x's in it. Right? So my f function is 3x plus x squared y plus y cubed plus any constant k. Does that make sense? It's kind of you have to do a couple steps with a couple integration maneuvers. Think of this like solving a puzzle, right? You have two pieces of information and you have to find one that matches both of them. So what you're doing here is finding a possibility for what it should be, and then you're checking that it matches the information you already have. Right? The other piece of information you have.
Can we try another example?
Yeah. Does this make sense?
I think it does.
Okay. We can do this in higher dimensions too. So be careful, let's see the word I'm looking for. Try to really remember the concept that we did here. We integrate, the key concept is each of these is the derivative with respect to a variable, right? So if I integrate one of them out, I should get f. But when I integrate one, I have to add the appropriate thing that could have disappeared.
You started integrating the p first instead of doing df dx. You integrated that. And
Yeah.
You could have done the other.
I could have
one
done the
too,
other one first if I wanted.
and you would have gotten the same answer.
We will get the same answer, yes. So let's look at that. That's a reasonable question. This is another example anyways. So we'll do the same example a different way. I'll write on a new sheet of paper. So Nick says, let's integrate this one first, right? So what should I integrate this with respect to?
X. Or
To
Yeah.
y.
to y.
Because this is df dy. Right? If this is df dy and I want to get f, I should integrate this with respect to y, right? Yes? Yeah. So I integrate this with respect to y. What do I get?
Y x squared plus
Y cubed. Just y cubed.
Y
just,
cubed?
y cubed.
Plus
Does this see
g of
anything else?
f of x
So
Plus
g
mx or
prime
g.
of x.
G of x.
Oh, g of x.
Right? This can be any function that has only x's in it. Right? So now this is f. What should I do now?
Find do the derivative in
Yep.
respect to like x.
Take the derivative with respect to x. What should I get, Yosin?
You should get 2x, and that's it.
Um,
Oh,
not quite.
What's g prime of x?
2xy. I gotta take the derivative here. Right?
oh yeah.
Plus g prime of x. G is a function of x.
Yeah.
And what's on this equal sign? What's on the other side of this equal sign?
On the other side, it has to be equal to 3 to the derivative of 3 plus 2xy. So 3, yeah, just 3.
That's it. This is df dx right here.
Yeah,
Right?
yeah, that's true.
So g prime of x is equal to 3.
G prime of x is equal to 3. So what is g of x?
3x.
Just 3x
G of x is 3x
plus k.
plus k, right? And k is now a constant, is a constant. So what is f? F is x squared y plus y cubed plus this, 3x plus k. And they're exactly the same.
That's
There. So doing them in any order doesn't matter.
This is how you tell if it's conservative.
No,
No.
this is how you find the function f that makes it, whose derivative is f, right? Checking if it's conservative is as simple as taking two derivatives.
But this is how you find f to do
This is
that.
how you find f to actually compute your integral using the fundamental theorem.
Interesting. What do you do with those constants then? They just disappear when you integrate? Or when you, not integrate, derivate?
Well, one, you don't derivate because that is not the correct word. But when you differentiate, yes, k goes away, right? That's exactly what happens with the constant. Right?
Yeah, okay, it does disappear when you integrate.
And if you think about this equation, let's just do an example. Okay, let's do integral c f. This is this f, right? dr, where c starts and ends at 0, 0 and 3, 1. Okay. So note, this is a conservative field, right? It doesn't matter what C looks like. It only matters where it starts and where it ends, right? So now, how do I compute this integral?
Well, if you found f,
Which we did, it's right here.
you plug in those points
Yep.
into f.
So what should I get? Tell me what I'm writing down here.
Wait, what was f equal to again?
It's right here.
So it should be, you should plug 0, 0 for your x's and your y's into that function.
Yeah, but this is, I start here and I end here. So I should put this one in first,
That
right?
one first, yeah.
So I should get 3 squared times 1 plus 1 cubed
Cubed
plus 3 times 3 plus k.
minus
minus
0 plus k.
0 squared times 0 plus 0 cubed plus 3 times 0 plus k, right?
And the k's, I guess, cancel
And the
out.
k's cancel.
Huh.
Plus k minus k. So what do I get? I get 1319.
What does that mean, though?
This is the work done
Ah,
by this vector field along any path that starts here and ends here.
oh, wow. That's cool.
Note, by any path. It does
And,
not
yeah,
matter
and,
where I go or how I get there, as long as I start here and end there. Okay?
So in the cases where it's not conservative and you wanted to find the work done,
I
how
would have to do it the old way that we did in section 6.2.
yeah,
I'd have to parameterize it. I'd have to take some derivatives and take some dot products and stuff like that.
do all that extra stuff. Okay.
Yep. But in this case, that's great. Here's another question. I like this one. I don't know what page we're on now, 12, 13, 13. So 14. Let's do the same thing. One last question. This is a short one. Y squared j. What is this integral? F dr c, where c starts and ends at 0, 0.
0?
0.
Yeah, you said it.
It's conservative, right? Because this is conservative, it doesn't matter what C does as long as it starts and ends at the same spot. So I don't even need to do any, I don't need to find what F is. I don't need to do anything. All I need to do is take these two derivatives, check that it's conservative, and write down 0. Okay? Does that make sense?
Yeah.
Next week, not next week, Thursday, we're going to talk about Green's theorem and some of the other theorems. We're going to start generalizing the fundamental theorem of line integrals up in higher dimensions. Okay, eventually moving to Stokes' theorem. And along the way, we'll see really awesome applications of this stuff to physics. Faraday's law is essentially this theorem, the fundamental theorem of line integrals. Right? You have a line integral over a closed curve, and you're integrating over the electric field, which is conservative, so you get 0. That's Faraday's law. Okay, it's just literally an example of this theorem. Okay, I forgot if that's Faraday's law or Ampere's law. It's one of them. One of them is electric and one of them is magnetic, but they're both integrating over closed curves over a conservative field, so they're both 0. Okay, I forgot which one is which, but they're both using the theorem we just talked about. Okay, please practice this thing. You're going to need to know how to find the function whose derivative is your vector field if it is conservative. Okay, so key takeaways. Quickly check if a field is conservative or not, and then how to find the function if it is. Okay.
You quickly check with the
You muted yourself.
wait, how do you quickly check again?
By taking derivatives, right? It's
Take the
theorem 6.
derivatives. Yeah.
So if you take derivatives and they match on a nice region, conservative. If they don't
Yeah,
match,
okay.
not conservative.
Not conservative. All right.
Okay.
Cool.
That's it. Sorry I kept you a little bit late. Have a nice day.
Thank you.